So from P21 upon C now, we will go to the other space groups which are possible in the monoclinic symmetry. I have indicated two space groups here. I have given the equivalent points diagram overlapping the symmetry points. So I want you to examine this equivalent points and the location of these symmetry points and make a guess of what could be this space group. The equivalent points of course are already given here. So making a guess of the space group is not going to be very difficult if we follow all the rules which we laid out in the case of P21 upon C, for example. So here is a case where you have a two-fold axis associated with the center of symmetry, and 1, 2, 3, 4 are marked here. The 4 equivalent points are marked here, and 4 other equivalent points are marked at this point. Now this refers to half along y and half along x. So this therefore now indicates the addition of half plus x half plus y tells us this has to be a C-centered system. So it is monoclinic and C-centered. So the 4 equivalent points are surrounding this particular point, and there is a two-fold axis coincident with this and a mirror plane which is coincident with the origin. What is very interesting is to see that apart from the presence of two-fold and this, we also develop a glide plane at 1/4. That is because if we work out the relationships between 1, 2, 3, 4 and 5, 6, 7, 8, we will see the presence of a 1/4 glide plane operation. So what is the space group? We have an indication that the lattice is C-centered. There are no marks of shift of the axis with respect to these positions. The two-fold axes are coincident with the origin, and there is a mirror plane which is perpendicular to that. What is very interesting is that you also develop a 2-1 screw axis between this point and this point, which is halfway removed, that is the centers of symmetries. You have the 2-1 screw axis also located. So at the outset the diagram looks very complicated. So many symmetry elements are shown here. For example, the 2-1 screw axis is shown, the glide plane is shown, the mirror plane is shown, the two-fold axis is shown. So how do we discern that the space group is whatever it is? One conclusion we immediately came by looking at these 4 and these 4 is that it is a C-centered lattice. So that means we should have an equivalent point corresponding to x, y, z, which generates number 0.5, which is x plus half y plus half z. So that means the C-centering is clear. So we have therefore a C-centered lattice. The fact that we have a point which is x bar, y bar, z bar tells us it has to be a centrosymmetric system. So if it has to be a centrosymmetric system and a C-centered lattice, the point group symmetry should be 2 by m. It cannot be 2, it cannot be m alone, and therefore it is a C2 by m kind of a symmetry operation. In fact, if you look at the first 4 equivalent points, you will see a similarity between this and the P2 by m space group, which we saw a few slides before, and therefore this is 2 by m and this is C-centered lattice. So the space group must be C2 by m. So the diagram here and the set of equivalent points, now we can verify that with respect to the occurrence of 2 by m. So since it is 2 by m symmetry, there are no translations that are required, and therefore the mirror, the two-fold and the center of symmetry, they intersect at 0, 0, 0, and the C-centering generates the one at half along x, half along y. What is very interesting is in this particular space group, because of the presence of center of symmetry as well as the C centering, we develop two additional symmetry elements. One is the symmetry element to one screw axis, which is 1/4 at this point, and the other is the glide plane, which is moved by 1/4. So, I want you to take it as a home exercise where you find out in what way this glide plane generates the equivalences of these 4 onto these 4. In other words, operate the C glide operation on one and see to which of the say 5, 6, 7, 8 it corresponds to glide plane operation. Likewise, you operate the 2, 1 screw axis about this point and see which of the 5, 6, 7, 8 associates itself with the operation of the 2, 1 screw axis. So, the interesting observation which we make here is, even though the space group is C2 by M, there are no movement of the translation involved components. We generate translation involved components as a consequence of the presence of the C centering. The C centering which gives rise to half plus x half plus y will automatically generate additional symmetry elements. Now, this is the beauty of crystallography. So, when molecules crystallize in such a space group, they get confined to not only obey the requirements of C2 by M as we have seen here, it also should obey the requirements of the presence of a glide plane 1/4 removed from the origin and a screw axis which is again 1/4 removed along the A direction. So, once we have any axis at 1/4, we will automatically have the same axis at 3/4, and that is what is marked here. You have the 1/4 and you also have the 3/4. Similarly, the 2, 1 screw axis appears at 1/4 and 3/4. So, therefore, the space group is C2 by M. And the next space group which I have indicated here, I want you to again examine it carefully and see what is your conclusion on this one. The conclusion on this one is a little complicated, but it is straightforward again. If you look at 1, 2, 3, 4 and look at 5, 6, 7, 8, it tells you it is a C centered lattice. The only difference or a major difference which you see is that the two-fold axes are now removed by 1/4. Since this two-fold axis get removed by 1/4, what is your guess? The guess is that there is a translation involved component in a direction perpendicular to this, and the component which can be perpendicular to this is related to a mirror. And normally in a monoclinic system, the component that is related by a mirror symmetry is the one which is now it so happens that it is the one which associates itself with the C centered lattice. And with respect to the C centered lattice, it is the one which is associated with a C glide plane. So, there must be a C glide plane now associated with this. So, the C glide coincides with the origin, two-fold symmetry moves by 1/4. This generates therefore the space group C2 by C. So, as you see by just looking at the presence of the equivalent points and the locations of the presence of the symmetry elements and the location of the symmetry element, you can determine the space group. And once you have determined the space group, you can write the equivalent points. And these equivalent point diagram which is shown here along with the presence of the symmetry information will uniquely determine the space group. And so, we get the space group C2 upon C. And that way at this juncture we will now go and try to examine the space groups more thoroughly. To examine the space group more thoroughly, there is no other method better than observing them through what we call as the international tables for crystallography. So, we now cross over to the international tables entry. A little story about the international tables because when more and more structures started getting accumulated, and it was required that the practicing crystallographers will have a direct access to the existence of the 230 space groups, their corresponding space group diagrams, the diagrams associating them with the objects, the diagrams that are generally associated with the equivalent points and so on. A listing of the equivalent point was also necessary, and as a consequence the international tables for crystallography was developed early 1950s. In fact, the first issue was I think issued in 1951, and that was called the Red Book because the color of the international tables was red. It has undergone many changes and metamorphoses, and at this particular time it is available online. So one can download the international tables and then look at the details of the space groups. So whatever we have discussed so far in terms of the space groups, in terms of the equivalent points, in terms of the special positions, in terms of the Wyckoff notation which we are going to introduce now, all these issues will be listed out under one entry in the international tables. So this is more or less the Bible for crystallographers in order to get all the details of the given space group. So suppose a crystal crystallizes in a given space group. Most often than not nowadays the possible space groups are indicated by the automatic machines on which data collection is carried out, and it is not required that you need to be a crystallographer if the space group is identified uniquely. But if the space group is not identified uniquely by the automatic machines, then I think a little knowledge on crystallography becomes essential. And this particular course is aimed at giving you that kind of knowledge as a background, so that you will be able to use the automatic machines within quotes automatically. That means you will now make use of these machines to the fullest extent possible, and in case the machine is not able to decide the space group, by examining certain details of the machine data, in principle you should be able to find out what is the space group. So in order to find out what is the space group, we should know how the symmetry elements are disposed in a given space group and how each and every object repeats itself based on the symmetry that is present in a given space group. We have studied the triclinic and the monoclinic systems thoroughly, and the study of the triclinic and the monoclinic systems have already enabled us to understand the logistics of how the objects find themselves with respect to a given space group. The thing which is missing from us at this moment is a complete knowledge of a given space group. What are the things which we need of a given space group, and can we make a list out of that? And that is provided by the international tables for crystallography. At this time we also will start introducing a new set of symbols which are up here, and these symbols are the ones which are referred to as the Schoenflies symbols. Are you able to see it? So these are the Schoenflies symbols. Spectroscopists, they do not use the nomenclature which crystallographers use. For example, in crystallography we use the point group information and also the lattice information, and combine the lattice information with the point group information to derive the space group, and this will be the space group nomenclature. This is referred to as the Hermann-Magwijn notation, and that is the notation we will follow throughout the course. I will provide you with a chart probably in the next discussion, where we can convert the Hermann-Magwijn notation to what is called the Schoenflies notation, and this Schoenflies notation is the one which the spectroscopists follow. So since P1 is a space group where there is no symmetry at all, in case of spectroscopic symbol the no symmetry is indicated by C1. C1 represents a rotation 360 degrees, and the one on top is the one which is now representing the space group. So if one wants to use the Schoenflies symbol and still use this nomenclature to represent the space group, then it is a C11. You will see what representation P1 bar will get when we go to the description of P1 bar. So this has to be borne in mind, because spectroscopists, and more often than not the practicing mathematicians who use group theory, they use this nomenclature more often than this nomenclature. This nomenclature is utilized essentially by crystallographers who look into the determination of structures, look into the details of structural motifs, and then look at the structure of the molecule inside the crystal lattice, and then the interaction of these molecules within the crystal lattice and so on. So, the requirement is that we should stick to the Hermann-Magwijn notation. So, in the rest of the course we will stick to Hermann-Magwijn notation, but for those spectroscopists and group theoreticians who would like to go into the detail of what is the corresponding symbol using the Swayam notation, they can refer to the international table again, or I will provide a diagram, and probably a handout also will be given by the TAs, which will show the conversion from the Hermann-Magwijn to the Swayam notation. So, this is the first entry of the space group P1 in the international tables. So, obviously the first number is 1 out of the 230 space groups. This is the first space group. P1 is the Hermann-Magwijn notation, as I mentioned, and the point group symmetry, which is mentioned here, is 1. So, the point group symmetry is 1, the space group is P1, and this belongs to the triclinic system. Now, something is written down here which we will discuss much later, but what it tells us is that there is something called the Patterson symmetry, which will have the same space group converted to P1 bar. So, if you look at the Patterson symmetry associated with P1, we will get P1 bar. Now, what is Patterson symmetry? We will be discussing this Patterson symmetry when we actually determine the structures of molecules inside crystal lattices in a later class. So, at this moment, let us say we will take this off from this projection and look at only these. So, P1 one fold symmetry triclinic. The international tables provides you 3 different projection diagrams depending upon the axis which we are choosing, which we have chosen, and generally this is the preferred projection, the first one, which is 0 A and 0 B. X axis down here and y axis that way. As I mentioned, that the positions of any object inside this is mentioned as a fraction of the B value and a fraction of the A value, and those are referred to as the x and y coordinates in this particular projection. It does not mean that this particular angle has to be 90 degrees. So, what you see as coordinates given in crystallographic analysis, you see the coordinates of the atom positions and so on when you read literature. In the research papers and the review articles and all that which you read, the coordinates that are given are those of fractional coordinates. Fractions of A and fractions of B now represent x and y. Similarly, the fraction of C represents z. So, when we say x, y, z as the position which is indicated here in the diagram below here, this tells us that there is a position which is for one particular object. In this particular case, just like the previous discussions we had, instead of a comma here a circle is used, and then there is a plus which indicates that the object is coming away from the board or away from this projection. So, if the object goes inside this, we indicate it by a negative sign. We will see what happens if we invert the object in the next projection where we discuss P1 bar. So, in P1 therefore, if you see the unit cell, this is the unit cell, it is divided into half and half here, and you see that the unit cell has only one object. So, that is the object which is a 360 degree operation, brings it onto itself. As we say, as defined earlier, the requirement of a space group is that the object has to come onto itself after the symmetry operation. So, in this particular case it comes onto itself, and so the origin can be arbitrary. We can choose the origin wherever we want in case of a triclinic system, and then we define what is known as an asymmetric unit. Now, the asymmetric unit in this particular case is the unit cell, because there is no other object. As we discussed, then z is equal to 1 in this particular case, and there are no special positions, no symmetry positions in P1, and therefore, the asymmetric unit is the unit cell. So, it is described as 0 less than or equal to x less than or equal to 1. Remember, these are the fraction coordinates we talked about. So, this is now A, B and C. The full value of A, B and C is taken. So, the value of x ranges between 0 and 1, the value of y ranges between 0 and 1, and that of z also ranges between 0 and 1. The symmetry operation that is present in P1 is only 1. So, this is a redundant set, and you see therefore this entry as the first entry for number 1 in the periodic table. Now, apart from that, the types of translational periodicity is indicated here. These are the generators selected, the translation along A, translation along B, and translation along the C direction, or these are the ways in which we can represent the translational periodicity in the unit cell. Now, the additional details which come here are the ones which we have to now learn carefully. The additional information which comes here, which is written here, can you see it in the back, these details clearly? Multiplicity, Wyckoff letter, and site symmetry. So, these are the three issues which we will be discussing in more detail as we go to the higher space groups. But in this particular case, the space group tells us about the multiplicity value, the Wyckoff letter, and the site symmetry. We will define these three when we go to P1 bar. At this moment, there is no entry associated with except this one, which tells us that the multiplicity associated with this object is 1, which refers to x, y, z. The Wyckoff letter is A, that is the highest symmetry which is present in this system, and then the site symmetry, the symmetry associated with any position in the unit cell is 1. So, there is no symmetry, it is 360-degree rotation. So, the equivalent points are written here, that is x, y, and z. So, there is only one equivalent point, and therefore, the required other issues associated with coordinates are not given. So, the coordinates are only one type, which is x, y, and z. So, P1 is the number 1 space group which has no symmetry other than the 360 rotation symmetry, and all the specifications which are given here fully qualifies this space group P1. On the diagram here, the symmetry diagram here, and then of course, the equivalent point positions indicating the number of equivalent points in the unit cell, which happens to be 1. The symmetry operation is also 1. Asymmetric unit is defined by the unit cell here, and then we have the definition 1A1 x, y, z telling us that there is no further symmetry operations that are possible in this case. The special projections which are indicated here tell you very clearly that along 0, 0, 1 what is the axis, along 1, 0, 0 what is the symmetry, along 0, 1, 0 what is the symmetry. This symmetry you notice is indicated with a little p and 1. The little p tells us that we are now talking about 2-dimensional projection, or in other words 2-dimensional lattice. This particular 2-dimensional lattice, which is in 3 dimensions triclinic, has a symmetry 1. Remember, when we discussed the 2-dimensional lattices, there was no third axis, and there the symmetry was P2. There was always a twofold axis associated with the lattice point. So, here the moment we introduce the C axis direction and say this is a 3-dimensional object, the corresponding projection diagrams will have only one object, and therefore, it is P1 in all the 3 cases, and the origin is taken at 0, 0, z. Z is arbitrary. So, we can say z is equal to 0, then this represents the diagram that is required. So, this diagram therefore has the origin at this point by definition. We have given z is equal to 0, it is arbitrary. Then this is the A value, the cell dimension, and that is the B value, the cell dimension along this direction. So, we are referring to this particular projection, and in this projection we have this object which is represented as x, y, and z. The value of z is now coming up from the board or from the projection. So, this now describes more or less the whole thing that is associated at this moment for us to note. There are other entries in the international table which at this moment we will not worry about, because we have to now fully understand all the 230 space groups in order to appreciate what are these entries. So, we will not worry about these entries at this moment. However, we are also not going to see all the 230 space groups in this way. We will take a few representative examples. so that we will now learn how to read the international tables. You see, for example, when you are taught the grammar of a language like in English, the grammar is taught with respect to the nature of the words, the way you can combine the words, the types of words you can have, the noun is talked about, the adjective is talked about, adverb is talked about. So similarly, we will tell all the language that is required in order to understand the grammar of crystallography in 230 space groups. The actual textbook which we write about each and every molecule will be different, but each and every molecule will have to follow this grammar book which we have prescribed. So we cannot go away from the grammar book which we prescribe, and therefore all the elements of the grammar, the way in which we make sentences, the way we make the combinations of sentences, the phrases becoming sentences, they all become very important when once we study the space groups. Afterwards, every novel can be different. Every crystal structure can its own beauty. Every crystal structure eventually with the molecular species inside can have its own story. It can have its own property and so on. So you can write an innumerable number of stories, and that is how the data accumulates in the understanding of a given molecular species. So then we can classify these molecules into various kinds of organic, inorganic, organometallic and so on, the categories. We will go into those details later. But at this moment we are looking actually into the grammar book. The grammar book which tells us how we make these combinations and how these combinations will give rise to sentences which are meaningful. So the next step would be to go to the next space group, which is number 2, which is P1 bar. P1 bar, you see the symbol now is CFI. The moment we use a small I in spectroscopic symbol or in group theory, it tells you the inversion center. I refers to the inversion center. So therefore we have the 1 bar which is indicated by the Hermann-Magwijn notation. In the spectroscopic notation is CFI. So group theory and the Hermann-Magwijn notation followers in spectroscopic nomenclature, they use CFI. And both of them now belong to the first crystal system, so it is 1. So this is Ci of 1. And the point group symmetry is 1 bar, as we already know, and this belongs to the triclinic system. Now how does the projection diagram look like, and where are the symmetry elements? So that is given in these 3 projections. Again, we will concentrate only on this projection diagram. Now this particular projection diagram tells us the presence of presence of A, which is now down this direction, and the presence of B, which is now in the horizontal. So the vertical down is the A direction. Remember, this is not 90 degrees. This is whatever is the angle between A and B, which happens to be gamma. For a triclinic system, A not equal to B not equal to C, alpha is not equal to beta not equal to gamma. And therefore we have this situation where we have now representing the projection diagram like this. The center of symmetry, as we discussed all along until the last class, the center of symmetry, if it is present in a crystal in a space group, it should be at 0, 0, 0. So we therefore move the center of symmetry to the origin. Once we have the center of symmetry at the origin, there is a center of symmetry at cell edges, and therefore all these cell edges develop the center of symmetry. And we have seen by the equivalent point distribution, which is shown here, the equivalent point distribution which tells us this is xyz and this is minus x minus y minus z. So this is the center of symmetry which is up here. So you see that in earlier diagrams where we studied, we put them together. Putting them together was easy for our understanding, and that is why we did that. But now we want to understand the symmetry positions differently from the positions of the objects, and that is why 2 different diagrams are given. So these 2 diagrams therefore are of crucial importance, this as well as this, which will tell us the symmetry position diagram here and the equivalent point diagram here. So you see that this is now centrosymmetrically going over there. So the negative value associated with this open circle is indicated by the presence of a comma inside. So this is now a comma inside the round representation, and a minus indicates that it is going down the plane. plus is up the plane, minus is down the plane, and apart from that the other values of x and y in this case, because this is the value of x, that is the value of y. So, this represents x, y, z. The value of x and y changes to minus x minus y, and that is why it is shown with a comma. So, whenever there is an inversion, the inversion is shown with a closed circle with a comma inside. So, this now will also tell us how the translational symmetry takes them up into these objects and invokes the presence of the center symmetry at this half along x, half along y, which is up here, and you see that these two, this comes by translation along this direction and translation along that direction, and so these two are related by a center symmetry. So, we will see the further details. The asymmetric unit now is what? The asymmetric unit now is half along the x. That means the asymmetric unit is only that much. The asymmetric unit is only that much because you have a center of symmetry here, you have a center of symmetry here, you have a center of symmetry here. Effectively, you can consider this as a unit cell, which is a subcell of this unit cell, and in that subcell there is only one object, and that is why we call it as the asymmetric unit. So, here the z value, the number of equivalent points inside the unit cell is 2, x, y, z goes over to x bar, y bar, z bar, and each of these blocks therefore now, that is why these two lines are drawn, each of these two blocks therefore now represent the asymmetric unit. So, the asymmetric unit is 0 less than or equal to x less than or equal to half, y is full and z is full. You can also interchange them. You can have this moving over to y and this moving over to z, and you can have other types of asymmetric units both in the y direction as well as in the z direction. But this is the definition of the asymmetric unit with respect to this diagram and with respect to the projection 0 AB, that is AB projection. Okay. Now, you see that the symmetry operations become 2. There is a symmetry operation 1 and there is a symmetry operation 1 bar, and this 1 bar symmetry operation is about the origin 0 0 0. And so, again the generator selected as before along the x direction, along the y direction, along the z direction. Now, the space group is number 2 as we have seen. Now, what happens? This is a very crucial stage where we have to fully understand the concept of multiplicity, the concept of Wyckoff letter, and the site symmetry. So, let us go through it a little carefully. Now, there is something on the right hand side for which we will return much later. This is with respect to the experimental conditions which get generated due to the presence of the 1 bar symmetry. Right now, we will not worry about it, so forget about it at this moment. What you have to remember is the fact that if there is a general position which is now associated with one symmetry 1, then there are two objects, x, y, z goes over to x bar, y bar, z bar. X, y, z goes over to x bar, y bar, z bar, and those are the two equivalent positions. So, z is equal to 2, z prime, which is now the asymmetric unit, is equal to 1, and the asymmetric unit we have already defined as the half the value along x or y or z. We can choose any one of them in this particular space group. So, having given that choice, we will now look at the so called multiplicity. Now, what is multiplicity? What is the number of the multiplicity that comes on the x, y, z? Suppose you take the coordinate as x, y, z, how many of equivalent points we generate? In other words, the number of equivalent points, the value of z. The value of z is represented here, which is equal to 2. So, multiplicity is how many such objects are there in the unit cell. We have an object located at x, y, z corresponding to x, y, z. How many such objects are located with respect to minus x, minus y, minus z. So, there are 2 of them. So, therefore, it is 2. The site symmetry is still 1. Wherever it is sitting, it is 1 only, because it is a triclinic system. So, the site symmetry is 1, but the multiplicity associated with the site is 2. So, that means if you have an atom at x, y, z, it has to have an atom at x bar, y bar, z bar. It depends upon where you define the origin. So, you go back to the figure here, you can define the origin wherever you want in this projection diagram. Correspondingly, all these centers of symmetries will move. the 0 will coincide with wherever we represent that, and the xyz value will be read based on the value of the origin, which is 0 0 0. So, suppose I move this to this origin, their representation is different, and therefore, the value of xyz will be different. With respect to the xyz here, therefore, we have invoked now several centers of symmetry. So, this particular xyz position, which is right here, the position with respect to that can be expressed 8 different ways. The 8 different ways are 1, 2, 3, 4, half removed 5, and then 6, 7, and then 8. So, totally 8 possible ways in which we can represent them, and those are listed here: A, B, C, D, E, F, G, H, and the positions of these centers of symmetry are indicated. What it tells is also the fact that if there is an object which sits at any one of these positions, the object is independent of the other positions. So, if you have 8 equivalent 8 positions here, these 8 positions which are generated due to the presence of the 1 bar symmetry, they have already built in them the 1 bar symmetry. That means every xyz will go to x bar, y bar, z bar is built onto them. That means if you take for example 0 0 0, operate this in symmetry operation x bar, y bar, z bar, you will get to 0 0 0 only. So, the 1 bar symmetry therefore is already inherent at that point. It is true with every one of these 8 points. 1 bar symmetry is inherent at that point. It resides at that point. Since the 1 bar symmetry resides at those points, these are referred to as special positions. So, we have 1, 2, 3, 4, 5, 6, 7, 8 special positions and 1 general position. So, the special positions importance goes as we have arranged here. We start from A, then we take the z axis half as the B, the y axis half as the C, and the x axis half as the D. This is the nomenclature which is now A, B, C, D now is referred to as the Wyckoff letter. Wyckoff used this symbol to identify the differences of atoms which can sit in these positions. For example, we can have an atom in 1 and some other atom sitting in let us say half 0 0. These 2 atoms are not one and the same, they are different atoms. So, structurally they are different. So, indicate the differences in structure, A and D are getting invoked. So, we say that suppose there is an atom 1 at A and atom 2 at D, we say that the structure is generated with the atom 1 at A and atom 1 at D. That means the 2 atoms are different from each other. In fact, if a same atom sits in these 2 positions also, their properties are different. That is because if you sit at 0 0 0, operate the center of symmetry, you get 0 0 0 again. If you sit at half 0 0, operate the center of symmetry, you get half 0 0, you do not get 0 0 0 or any of these 8, and that way they are very special. So, these positions therefore are referred to as special positions. Wyckoff decided to follow a certain protocol, and that protocol is generally followed. For example, in this case we start from z, y and x, and when we have 2 of these values equal to half, we start x, y, x, z and y, z in that order. And this order depends also upon the other symmetry elements which are present in the space group. If we go to higher space groups, this order need not be followed. We will see that as and when we examine the other space groups. But in a triclinic system, we have 8 special positions, 2 general equivalent positions, 8 special positions, and they are indicated with the Wyckoff symbols A, B, C, D, E, F, G, H for the 8 special positions and I, which is a general position. So, the number of value of Z is 2 in case the atoms or the molecules or whatever is sitting in general positions. So, in general positions the symmetry is 1 and therefore, it will generate its x bar, y bar, z bar. So, we will have 2 objects generated. So, any object sitting in any of these special positions will generate only 1 object. That means, the object must itself possess the center of symmetry. So, half of the object, the other half of the object, they should be related by a center of symmetry. Then and only then the atoms can sit at those positions in this example. So, P1 bar therefore already is looking very complex in the sense of understanding, but it also tells us that it is now given special occupancy positions for special issues. So, for example, let us say you have an organometallic compound and you have a metal which is sitting at one of these Wyckoff positions. The rest of the atoms need not sit at that position, but they should sit in such a way that the overall symmetry associated with the molecule is centrosymmetric. Otherwise, the heavy element, the metal, cannot sit at any of these special positions. So, imagine a situation where the metal atom is sitting elsewhere. The moment the metal atom sits elsewhere, even though there is a center of symmetry which might be associated with the molecule, which is a very rare chance, the metal now will generate another unit which is going to give us Z equals 2, and therefore, there will be two objects. So, let me repeat, if you have a metal organometallic compound. So, there is a metal and then organic surroundings. The metal will sit, let us say, at a special position, because the atom by itself has a center of symmetry. It is not just the atom we should consider, we should also consider the bonding associated with it. The nature of the bonding and the way in which it is bonded to other atoms, the environment should also be centrosymmetric. So, the molecule may find itself in a centrosymmetric environment, but it is not necessary that all these atoms have to sit in this special position. So, they will be sitting in their general positions. When we look at the realistic structures later on, we will see how this really happens, even though it is very interesting to notice that this can happen with respect to the way in which these things appear. Suppose there is an atom which is sitting here, and let us say this occupies any one of these centers of symmetries. If that is a spherical atom, let me make it a perfect sphere if possible. Okay. Now, it is nearly spherical. So, let us say this is our organometallic element, then whatever is the surrounding organic, let us say there is some branch coming out like that. Okay. Now, this branch should be identical to the coming out branch. So, these two should be centrosymmetrically related to each other. But you notice that if the coordinate of this is, let us say, 0 0 0 and the coordinate of this is x1 y1 z1, then the coordinate of this will be x1 y1 bar z1 bar. So, these two are now related by a center of symmetry. That means there are two objects, they are sitting in general position, and the x y z is equal to and x bar y bar z bar is getting generated. This is a possibility. Then the metal can sit in the special position. Suppose there is a structure in which there is a perfect center of symmetry, they can sit in any one of these positions. You notice that if this is not at 0 0 0 or some 0 half half, then the coordinates will accordingly change with respect to 0 half half. So, this molecule now will be only present with respect to 0 0 0, and that molecule will be present only with respect to 0 half half, which is where the metal is going to sit. I think this is a place where is a good place where we can stop today, and then we will continue tomorrow. Okay.